Good morning, good afternoon, good evening, depending on where you're joining us from. Welcome to this webinar on deploying stateful sets in Kubernetes. My name is Janakiram. I run my own company called Janakiram and Associates, which is based in Hyderabad, India. Apart from advising startups and working with various entities, I'm also a Google developer expert, primarily focused on Google Cloud Platform and Kubernetes. We have been running this series for a while. This is actually our 7th webinar on Kubernetes, where we cover various aspects and various topics related to the open source container orchestration engine. So if you have been attending the webinar series, you are pretty much familiar with what we cover and how we bring various aspects to you. But for those of you who are joining us for the first time, the Kubernetes webinar series is a monthly webinar focused on helping you get started with Kubernetes. The idea is to involve the experts from the container ecosystem with each webinar introducing a specific concept that would help you in accelerating your learning towards Kubernetes. We don't expect any specific prerequisites, but understanding of Docker would certainly help you. And we also try and give away $100 Google Cloud Platform credits. The recording of this webinar would be made available at cube.live, the same portal where you registered yourself for this webinar. So keep an eye on that, and you would actually see the recording showing up on the same portal in a couple of days. So let's get started. This is the 7th in the series, and this time we bring you StatefulSets, which are a pretty exciting mechanism to run stateful workloads on Kubernetes. So I have a pretty packed agenda for the day. I'm going to give you an overview of stateful sets, what problems do they solve, and how you can exploit that for deploying highly available stateful pods. And then we will take a closer look at setting up the storage infrastructure for running stateful sets. And I'm going to run a MySQL cluster in high availability mode configured as a stateful set. We'll then look at how we scale the stateful set, and then we deploy a content management system, a very popular one, which is WordPress, that leverages the MySQL cluster. Like most of my previous webinars, this session has fewer slides but more demos. And the good thing is the entire source code of the scripts, the Kubernetes artifacts, and the configuration guide is available to you on GitHub. I'll share the link towards the end of this webinar. I've also authored a step-by-step guide that was published at the New Stack a while ago. I'll also leave a URL that you can follow for replicating the same environment in your test bed or your development environment. So let's get started. As you know, containers are primarily meant for running stateless applications. Even today, it is pretty challenging to run stateful applications like relational databases or NoSQL databases or big data workloads. That's because initially when containers were created, the whole architecture was focused more on scalability and keeping the state away from the containers. While it does work for elastic workloads and stateless frontends, it throws a big challenge when we need to containerize existing stateful applications or migrating traditional applications to containerized platforms like Docker or Rocket or Kubernetes. So since containers use ephemeral storage, the content or the data that is stored also becomes unavailable when the container gets terminated. That is the default behavior. Kubernetes tries to solve that problem by making pods stateful. You can mount volumes. And as we discussed in the previous webinar, where we looked at host-based persistence and distributed storage-based persistence, you could leverage one of those storage classes to either use the underlying host infrastructure for storage, or you could also create an NFS or a cluster-based distributed storage on which you can mount volumes that are exposed to the pods. But that alone is not sufficient. There are a couple of more challenges that we need to overcome before we emulate a traditional either bare metal based or a VM based infrastructure on Kubernetes. It basically translates to the lack of stable naming convention, because as you would have seen, the pods on Kubernetes get an arbitrary name, particularly when you are deploying them as a replica set or a replication controller. That makes it very challenging for creating a cluster. For example, creating a master slave configuration or creating a replicated active-active cluster running on top of Kubernetes. And also creating a stable persistent storage per pod is not something that is inherently available within the orchestration engine. So mounting volumes is one thing, but creating an exclusive persistent storage backend per pod with predictable performance is not something that's been available within Kubernetes. So that's where StatefulSets help us by solving some of those problems. One of the core tenets of Kubernetes is high availability of applications. And that is fundamentally delivered through the concept of a replica set. As we have demonstrated in some of the previous webinars, you could package a replica set and define how many minimum number of replicas you need to run. And Kubernetes will ensure that at any given point of time, those many number of pods are always running. Even if the pod gets killed, or actually the node that is hosting the pod gets terminated or becomes faulty, Kubernetes will be intelligent enough to ensure that the desired configuration as mentioned by the replica set is always maintained. But that is for stateless workloads. How do we bring the same kind of high availability to stateful pods or stateful workloads? So that's exactly where a stateful set will be useful. So the idea is to bring the high availability of replica sets to stateful pods, which will enable us to run pods in a clustered mode. So that makes it possible for us to create active passive instances of databases or master slave configurations or anything that requires a coordinated deployment where you have multiple nodes coordinating and collaborating to ensure higher availability. This is ideal for deploying highly available database workloads, maybe running a Cassandra cluster or a MongoDB replica set or a MySQL active-active or active-passive cluster or a PostgreSQL cluster. Any of those can be easily configured as a stateful set. It's valuable for applications that need certain attributes. For example, stable, unique network identifiers. As we discussed earlier, pods get assigned an arbitrary name, which makes it very hard to maintain a well-known endpoint. And on top of that, the IP addresses keep changing. For example, every time a pod gets scheduled or rescheduled, its IP address changes. There is no guarantee that the pod would retain the same IP address. And on top of that, the name of the pod also keeps changing as and when it gets scheduled or rescheduled. Of course, we can use services, but that actually requires a different configuration. So we don't need to deal with multiple pods pointing to a service, but we need very predictable, consistent naming convention right at the pod level without relying on a service per pod. It's also valuable for applications that require stable and persistent storage. Again, we need to have dedicated storage per pod. So we don't have conflicts, we don't have overrides and other issues that might lead to data corruption. And of course, we should have some kind of consistency in the way the provisioning or scheduling of the pods are done. For example, in a master slave configuration, we ideally want the master to be set up first and then deploy multiple slaves and start replicating the data. And when we terminate or when we delete the deployment, we would first want to terminate the slaves in the order they are created before the master gets terminated. So we need some kind of a predictable sequential way of deploying and scaling, as well as deletion and termination operations. So stateful sets deliver on these capabilities. Currently, it's a feature that's in beta, which means it's not available in versions less than 1.5. But if you actually clone the GitHub repo and set up the stock Kubernetes repo on your own machine, or if you use Google Container Engine, you can actually play with stateful sets. So some of the key concepts include the creation of a headless service. So all the pods that are belonging to a specific stateful set will rely on a headless service. So the headless service is not pointing to a specific pod or to a specific endpoint, but it acts as the bridge between the pods that are clustered or that are created as a part of the stateful set. So it acts as the pointer that will bounce off the packets that need to flow between one pod and the other. So it is the internal DNS service, if you like, which is going to basically resolve the names of one pod to the other. So it just makes it easier for the pods to communicate with each other. And then each pod gets a DNS name that is accessible from any other pods that belong to the same set. So this means you can predictably create a master-slave replication, or you can deploy an active-passive cluster. Of course, the underlying storage infrastructure is still pretty much based on persistent volumes and persistent volume claims that we discussed in the previous webinars. And every pod that we create as a part of the stateful set gets a consistent ordinal index, which starts with 0, 1 and goes on to the maximum number of pods that you configure as a part of the stateful set. So it makes it very predictable. And pods are created sequentially, which means you can first create a master followed by multiple slaves. So again, it brings in more predictability and consistency. The identity is consistent irrespective of the node that it's going to be provisioned on. So it doesn't matter which node the pod will eventually land on or gets rescheduled on, but it will consistently maintain the same naming convention. So you can always reach the pod using the consistent naming convention. Pods are terminated in last in, first out order. So that means if you terminate or if you scale down a stateful set, the most recent pod that was created is the first to get terminated. So this will ensure a very graceful mechanism of bringing down your cluster without corrupting the data or without causing any issues with the leader election. So those are the key concepts. And as I mentioned, we have a pretty complex demo, covers the end-to-end configuration. So I'm going to jump straight to that. But before that, let me set the stage. So I'm going to start from the very basics of showing you an NFS backend that is running on my Kubernetes cluster. And then we go ahead and create the Kubernetes storage infrastructure based on persistent volumes and claims. And then we deploy an XD cluster. Why do we need that? Because we are actually using a specialized version of MySQL from Percona, which is called Percona XtraDB cluster. And that uses XD for discovery. So every time a new node comes up, it basically registers with XD, and the master will get to know that there is a new slave that's being created. So XD is going to be the discovery's backend for all the nodes of Percona XtraDB clusters to talk to each other. So we need to first deploy XD cluster. And while I do that, I also want to show you a concept called node affinity, where I ensure that each pod of XD is deployed to a specific node. So that will ensure that there is an XD backend available on pretty much every node, irrespective of where the Percona database pod will run. So this will serve two purposes. One is to show you how to use node affinity. The second one is it will ensure that at least one HT pod runs on each node. Of course, it doesn't really matter. You could pretty much push all of them to one node, or you can spread them across, but it makes more sense to run one HD pod per node. And with that in place, we go ahead and deploy the actual MySQL cluster, which is delivered by Percona in a high availability mode. And with the database backend in place, we go ahead and deploy a WordPress replica set. And since WordPress is a stateful content management server, which requires a file system that should be accessible to all the pods, we actually mount the storage on NFS. So that means even the static content like images and various other configuration files that WordPress expects is also going to be separated from the pod. Since that runs on NFS, the WordPress pod becomes absolutely stateless. The database is a MySQL cluster, the static content is on NFS, and that would make WordPress absolutely lightweight and stateless, and we can scale them very easily with a replica set. And there I want to show you how we can configure a feature called HPA, or horizontal pod autoscaling, which pretty much works like EC2 autoscaling. You can define some kind of matrix that will trigger an autoscale operation, either scaling out, which means you will run more number of pods, or scaling in, which means we will reduce the number of pods. So we are packing quite a few capabilities and features into this demo. And for a detailed walkthrough and to access the GitHub repo, visit tinyurl.com kubeSS, and you will be able to follow the step-by-step guide. So with that, let's get started with the end-to-end configuration of StatefulSet. All right. So let me first walk you through my current setup. So I'm using the stock Kubernetes deployment straight from GitHub repo, and let's get a sense of my infrastructure. So I have 3 nodes and 1 master, and all of them are currently running on Fedora, and this is based on Vagrant, so it's running on my local environment, and it is running the latest version, which is 1.5. So with that, let's first take a look at the NFS configuration. So I'm going to SSH into the master VM, which is running the API controller and all the master components of Kubernetes. Let's verify the actual NFS setup. So when you look at the etc exports file, you notice that I'm exporting the directory which is opt data, and this is the CIDR that I am allowing the access, and there are some standard parameters that I need to pass. So let's go to opt data, and I have 2 directories here. One is called content, the other one is called wall. So wall is designated for running MySQL StatefulSet. You will actually notice that there are 3 directories created with 0, 1, and 2. There is a specific reason why we follow that convention. I'll come back to that in a second. But you get an idea on how we're configuring NFS. This is a pretty straightforward NFS configuration on any Linux distribution, whether it is Fedora, CentOS, or CoreOS. The content directory is where we are going to eventually store the WordPress static content. So having inspected the master, let's get into one of the nodes. So currently I'm running 3 nodes and 1 master. So a Vagrant status shows us that we have 3 nodes running. So let me SSH into one of the nodes. All right. So let's look at the FS tag, which will show us that we are mounting an NFS share coming from the master server. 10.245.1.2 is referring to the master, and this is the export folder that we created on the master, and we are mounting this as data. So when we come to the MNT data, we notice that the same folders or directories that we have seen on the master are available. And this is accessible pretty much to every node in the Kubernetes cluster. So this is the baseline storage configuration for our demo setup. So we have an NFS that is configured across the cluster. The NFS share is exported from the master, and every node has a mount point to that. So with that in place, the very next step is to basically create the pods. But what I'm going to do is I will launch my kubectl proxy, which will give me a nice dashboard view. So if I visit localhost 8001 /UI, this shows us the Kubernetes dashboard. It's a pretty interactive and useful mechanism to check our deployment. So let's leave this as is and proceed with our demo. So now that we have the NFS in place, it's time for us to create the Kubernetes storage infrastructure. And when I say Kubernetes storage infrastructure, I basically mean persistent volumes and claims. So let's take a look at the PVs and PVCs. So if you have attended my previous webinar, you are familiar with the persistent volumes and claims. So here I'm creating a persistent volume, but instead of creating an mtdir or a host path, I'm actually using NFS as the storage class for my persistent volume. So the path is opt data /vol/0, and the server is coming from the Kubernetes master. So this is how I'm basically creating a persistent volume. Then I go ahead and create a claim, and notice that the claim doesn't know where the backend is coming from. It is transparent to the underlying storage. I could pretty much use Gluster, Ceph, or anything, but the persistent volume claim doesn't care about it. I also want you to carefully notice the naming convention. I'm calling this MySQL PV0, and that is pointed to vol/0 directory. And the claim is also called DB MySQL 0. So we are following the same naming convention that the stateful set expects. So the ordinal number, the index that we are using here, has a significance because eventually when we create the stateful set, it expects the same naming convention to be made available. So we create 3 different persistent volumes, 0, 1, and 2. And we also create the corresponding persistent volume claims that help us expose the storage backend to our pods. So this is the first step where we bring NFS into Kubernetes. So let's go ahead and create the volumes. All right. So now it has created everything that we need. So let's get the persistent volumes, and as you notice, it has created 3 volumes. And if we actually check the PVC, which is the persistent volume claim, we notice that they are bound to the volumes that we created earlier, and I have allocated 1 GB, roughly 1 GB of disk space to each claim. So this is the foundational aspect of statefulset. The key thing to understand here is the naming convention that we are following all the way from the directories till the PV and PVCs, right? So /vol/0, 1, 2 are mapped to PV0, PV1, and PV2, and they are further associated or mapped to things like DB MySQL 0, 1, and 2, which are basically our claims. So with that in place, let's go ahead and create the XD discovery service. So that's the most essential aspect or the component of our deployment, and it has some quirks that we need to understand. So let me show you how we are going to deploy a 3-pod XD cluster. As I mentioned, this is essential for Percona XtraDB cluster to discover the nodes. So we first start with a service, and this service exposes three ports, 2379, 4001, and 7001 for all the internal clients to talk to the XD backend. So these are the ports to which the MySQL cluster will start sending the requests. So we are exposing that, and this is an internal endpoint. So this is basically using the cluster IP, not exposed to the outside world. For debugging and to make sure that XD is up and running, I am also creating an external facing service, which is a node port type. And we are using this port, which is 30,001, to which I'm going to eventually send a curl request or a HTTP request, and it will come back to me confirming the installation of XD. So that's the only purpose. In production, this can be completely removed because you never want to expose XD to the outside world. So with the services in place, we go ahead and create pods, and we create exactly 3 pods. So we have the first pod, which is named as XD0. This is not a stateful set, but it's a good idea to follow the same naming convention. And it uses various command line parameters to bootstrap the XD cluster. So we configure the standard pod parameters through the command. The image is coming from CoreOS, quay.io. We are exposing certain container ports, but the most interesting aspect of this is the node selector element. So the node selector, when I say node 1, it basically ensures that the first pod is going to be scheduled on node 1. So once we create the first pod for XD, we need to create a service just to expose that. The way the XD service is architected, it is the only way for you to expose it. So what we do is we create a per pod service, which is going to be exposing only that specific pod. And how do we ensure only this pod receives the traffic? So we are using the label called XD0 with the selector called XD0. So we are basically exposing this pod through the service that we are creating here. We go ahead and do the same thing for remaining 2 nodes of XD. So we are creating the second one here, and this is going to be scheduled on the second node. And we again created a one-on-one mapping between the service and the pod, and we do the same thing for the third one. The key thing to notice here is the way we are ensuring that there is affinity. So all of them are going to be placed on the nodes that we are selecting explicitly. So this is going to result in the creation of 3 pods and 3 services attached to each pod, and then it creates a generic service which is going to be used by the MySQL cluster, the very first service, and then it also creates an external facing one purely for debugging purposes. So we'll end up creating 3 pods and 5 services. So I hope that's clear. The per pod service is meant for internal communication among the pods, and this service is meant for MySQL to talk to the XD backend, and this is purely for debugging purposes. All right, so let's go ahead and deploy the XD cluster. So this quickly creates 3 pods, XD0, 1, and 2. They are completely stateless. We need not even expose any volumes or mount points to it. Let's also check out the number of services that we got. So kubectl get service. And now you'll actually notice that there is an XD meant for MySQL's communication. Then we have 1 service per pod, and we have 1 for debugging and external communication. Now, how do we ensure that this is actually scheduled on the nodes that we wanted it to? So let's use the dashboard for that, which is more visual, which makes it more easy for us to inspect. So we have these 3 pods. Let me increase the font size. So we have 3 pods. So let's look at XD0 and these are the logs, but I'm looking at accessing the actual node configuration from this. Okay, so here it is. So this is the node on which the first XD pod has been scheduled, Kubernetes node 1. Now if we go back and look at XD1, that went to node 2. And here we have node 3. So essentially we managed to deploy one XD pod per node by explicitly creating the affinity. So that's the feature that I wanted to demonstrate. All right, so with everything in place, it's time for us to test if our XD cluster is up and running. So for that, what I'm going to do is to run a simple curl command pointing to one of the nodes, and because we are exposing port 30001 to the outside world. Oops. Let me make sure we are using the right port. Okay, so this is the port that I'm supposed to use. Okay, so now it actually sorry for the typo. So now it actually created a simple key with hello, and let's also access this with the appropriate port. I shouldn't miss that. So let me access that, and now this is coming back with hello, right? So this is the confirmation that XD is up and running, which is pretty good, right? So we have the XD infrastructure in place. With that, it's time for us to go ahead and deploy MySQL as a stateful set, and this is where the heavy lifting takes place. So let me walk you through the stateful set definition. So we first create a headless service, and this headless service is going to be actually used by the internal MySQL pods, right? So this is going to be used for all the pods not to communicate with each other. So it's a standard service. It's just that I'm pointing cluster IP to none, which means this service will never have a virtual IP. It is just going to be an intermediary that is going to connect one pod with the other when they need to communicate. I also create a node port for our stateful set. Again, this is purely meant for debugging. I don't mean to really use it in production, but this is just to make sure that our stateful set is up and running. So once we have these two service definitions in place, we actually define our stateful set. So the API version is going to be apps v1 beta 1, which indicates the kind of workload. And then the kind is not replica set or a pod. It is basically stateful set. And the metadata, we are configuring it to MySQL. But the actual spec starts from here. And here we say service name is MySQL, which is binding the service to the very first headless service that we created, which is also called MySQL. So this is the link between the pods within the stateful set and the headless service that we created earlier. And I'm launching 3 different replicas. You would actually notice that this definition is very similar to a replica set, except that this is going to be much more stateful in terms of its DNS name and the storage that's going to be associated with it. All right. We also use some additional parameters in this spec, like the termination grace period, seconds. But after that, it's a pretty standard definition of the pod with containers and volume claim templates. So here we create the actual container So the image is coming from Percona Lab. A big shout out to Percona Lab for creating a phenomenally powerful Docker image for deploying a Percona cluster on Kubernetes. Actually, you can also deploy this on any other infrastructure, but they have done a phenomenal job of packaging it the right way. We expose port 3306 because that is the standard MySQL port. And then we inject certain environment variables. For example, this is the MySQL root password. This is the XD cluster. It's going to rely on it for discovering the nodes. This is the extra backup password in case you are using that service, completely optional. The cluster name is Percona. This is the name through which the discovery actually takes place. So you want to mention that it's a mandatory value or the parameter. And then we go ahead and create volume mounts. So the volume mount name is DB, and it is pointing to where libmysql. This is basically the directory where MySQL is going to store its data files and log files. Now, having done that, we take a closer look at the actual volume claim template. And from this definition, you can't really make out that it's actually a stateful set because it follows exactly the same convention as the standard pod volume claim template. So we give the name of this as DB. We define the access mode, and we ask for 1 GB of storage. So since we already created the persistent volume and persistent volume claim, it's automatically going to get associated with it. And the beauty of this is the association of each stateful pod with the appropriate volume claim. For example, MySQL 01 will be automatically bound to MySQL PV01 and PVC01, so that there is a one-on-one mapping between each stateful pod and the claim, volume, and the directory that we have created. So it actually cascades all the way up to the pod using the same naming convention, right? So that is it. It's a pretty straightforward mechanism. We create one headless service. Optionally, we create an external facing node port service, and then we go ahead and define the stateful set. So we are asking for a volume claim template, which is going to be looking up for the claim that we already created, and it's going to pick up from that. Okay, so this is the crux of the actual stateful deployment. So let's go ahead and deploy MySQL. So kubectl create MySQL. That's it. So now it resulted in the creation of a MySQL service internally, which is going to be used by WordPress to reach the stateful set. And to test the connectivity and if everything is in place, we also created the MySQL client endpoint, which is basically a node port service. And it created a stateful set called MySQL. So let's get the pods. And now we have XD running, and then we also have MySQL 0, 1, and 2 running. So let's access the logs for one of the stateful pods. So this is still getting configured. It's going to take a few minutes for the entire cluster to get in sync and to stabilize. So let's access the logs of other nodes. So as you notice, they are currently establishing the communication, and very soon they will completely get in sync with each other, which means our cluster is up and running. We don't have MySQL 3. So we'll give it a few more seconds. So now member 2.0 with MySQL 2 is synced with the group. Let's check out the master that is also in sync. This is in sync, and this is going to get in sync very soon. So let's come back to the dashboard and explore this a little further. So when I click on stateful set, it only shows one stateful set with name MySQL. But when you actually drill down further, you notice that there are 3 pods that are consisting of this stateful set. It is these are all the logs, and as you see, it is still referred to as a pet. In fact, the previous nomenclature for stateful set was pet set. So some of the internal references still point to a pet set. Excellent. So now we have the HD backend and MySQL in place. So let's look at the services. So kubectl get services. And now we have a service which is exposed at 30,002. So what I want to do now is to check out the MySQL connectivity. So for that, I'm going to run a simple MySQL command, right? So I'm going to run this in loop, and we're going to talk to the MySQL PerconaDB cluster. So this is the host. I'm pointing to one of the Kubernetes nodes. The port that we are exposing is 30,002. I'm using the standard username password, and getting this number of replication node addresses will show us whether we have successfully configured the cluster. So let me go ahead and run this. If everything goes well, we should see 3 different IP addresses, right? And there we go. So 10.256.30.7 is basically one of the pods, and this is the second. Looks like currently only these 2 pods are serving. No, we have the third one. The 95.3 is the third MySQL pod that is actually serving the request. So this command that we just ran is going to get the node address of the host that is running on the IP address, and depending on which PerconaDB cluster it's going to run on, it will return the underlying IP address, and that's the reason why we see one of the addresses from the pool of the pods that we are running. So this is a proof that everything is set up, and we are now ready to run our workload. That's not all. So let's now log into the master, right, and get to the actual directory where we are storing this. So we go to opt data wall, and let's go to this, and there we actually see the data files and log files, and that belongs to the MySQL 01, right? Similarly, when you go to the next directory, this belongs to the second pod, and since the data is centrally stored on the NFS mount point, it is okay for us to kill one of the stateful data sets, stateful sets. So let me get the pods, okay? So I'm going to kill the stateful pod, right? So let's go ahead and kill MySQL 2, delete pod, okay? So now MySQL 2 got deleted, it is getting terminated, and if you actually run this in a wait mode, you'll notice that in just a few seconds, in the last 4 seconds, whatever we terminated got back, and it assumed the same name, which is MySQL 2, and it gets mounted to exactly the same directory that the previous pod was using, so it didn't lose any state. That is the beauty of StatefulSet. So let's try one more time. So I'm going to now delete MySQL 1 pod, and let's see how it gets terminated and how it comes back. And now MySQL 1 got terminated, it got created, and now it is in running mode. And very soon it starts syncing with rest of the pods, and we have the full-blown cluster in place. All right. So with that, we are done with the core, which is the deployment of StatefulSet. It's now time for us to deploy the WordPress replica set. So let's take a look at that. That is pretty straightforward. So I want to show you how my WordPress definition looks like. So I'm going to create a service which is going to expose our WordPress to port 30,000. And then I also create what is called as the horizontal pod autoscaler. This is a new feature. as I mentioned, it works exactly like EC2 autoscale. So I define the name of the replica set, number of minimum replicas, which is 5, max is 10, target CPU utilization percentage is 50, which means when the average CPU utilization of all the pods goes beyond 50, the autoscaler will kick in and it will create additional number of replicas till it reaches the threshold that we mentioned. After that, it's a pretty straightforward replica set definition. So we are starting with 3, and we are actually pointing var w3 html to my wall, and this is coming from MNT data content. And here what I want you to notice is we are actually not creating a persistent volume and a persistent volume claim. Instead, we are directly mounting it on the host path. And this is perfectly fine because MNT data content is not specific to a host. It is actually coming from NFS, which means a pod that gets scheduled on any node will have consistent access to this mount point. So it doesn't really matter. And of course, we are binding the database through the environment variable. WordPress DB host is pointing to MySQL, which is what we defined here as the MySQL service. So the state is now split between the database and the file system, making WordPress in itself completely stateless. All right. So with that, let's go ahead and deploy WordPress as well. So create -f WordPress, and it created 3 different entities. First, it created a service for the outside world to access the content management system. It has gone ahead and created the horizontal pod autoscaler called WordPress scaler, and of course it created the replica set. So now let's check out the number of pods. So now we have the perfect deployment in place. 3 XD pods for the service discovery, 3 MySQL pods running high available cluster of MySQL, and we have 5 stateless pods of WordPress pointing to the /mnt data folder of each node. And this makes it perfectly complete. Okay, I see some errors. It is due to the image pull issue. I also occasionally run into issues when I'm killing a MySQL and launching it again. That's the reason why you see crash loop back off. I need to debug that. But let's try and access. But I'm not too sure if we can actually access WordPress because one of the MySQL pods is it's not ready. But let's go ahead and give it a shot. If we hit any of the running pods, we might actually see the all right, so there we go. So that's WordPress running. Let me move this to Chrome. This is the browser that I use for demos. So we should now be able to access WordPress from this, and everything looks good. So now I can go ahead and set up WordPress. And now when we go back to the master node, look at the content directory under data. We see the WordPress files there. So that means the pods have started to use this as the location for storing the static content, which is pretty cool. So that's the full-blown setup, all the way from NFS to a horizontal pod autoscaler. This is one of the heavy metal sessions that I have delivered in this series. So that brings us almost to the end of this, but I want to announce my next session of this webinar series. We are very excited to bring you config maps and secrets. So I'm going to pick up another traditional application that requires pretty complex configuration, and we'll modify it for Kubernetes and deploy it. So on March 28th, same time, we will bring you the next installment of the series. where we talk about using config maps and secrets. Secrets are also pretty powerful. They decouple sensitive content from the pods with your applications by using a volume plugin. So we'll actually use a powerful scenario to demonstrate how you can use config maps and secrets. So in a day or two, cube.live will get updated, so you can register. We'll send you a reminder. And don't forget, it is tinyurl.com/cubess for accessing the complete tutorial, step-by-step guide, and the GitHub repo. When the video is ready, we'll also send you the link to it. So it's time for me to take a few questions. So before that, I need a favor from you. It will be great if you can tell us how you like this webinar. So I'm going to launch a poll, and I appreciate if you can take a minute and respond to this. Your feedback is highly valuable. Excellent. I'm only seeing 70% of you participating in the poll. I really appreciate if everyone can take time to participate in the poll. It would help us streamline the content and deliver better content for you. Excellent. All right, looks like most of you like this session, which is very encouraging. Thank you again. And it's time for me to look at the questions. Okay, there are just a few questions. So, okay, so this question is from Samir. What are the advantages of running a HA production database in Kubernetes as a stateful set versus RDS? Well, you can run databases in managed environments like RDS or Azure SQL database or Google Cloud SQL, but there are scenarios where you want to keep your data closer to your pods. For example, when you're creating a MongoDB replica set for capturing logs or for capturing data that needs to be closer to your compute, for example, closer to your web app, then you have to run stateful workloads within Kubernetes. So to reduce the latency and deliver high performance, which is just close to your application. So that is a scenario where you would want to run databases in Kubernetes, and StatefulSets just make it easy for you to run those relational and NoSQL databases. But other than that, if you have no specific reason to run StatefulSets and you already have a highly available database cluster running in RDS or a set of VMs, you are free to use. For that, you need to use a headless service. In fact, I'm going to cover that in one of my upcoming webinars on how do you integrate Kubernetes with traditional applications. So let's say you already have an Oracle database, and how do you create a Java application that runs on Kubernetes but talks to your existing Oracle database? So that's a different pattern altogether, but you can pretty much run. As I mentioned, the use cases are slightly different. So there is another question by Tiago. The XD mentioned is something the same that's being used by Kubernetes? No, I'm not actually using the XD that comes with Kubernetes. I don't want to mess with the system service discovery backend. So I ended up creating my own XD cluster dedicated to the deployment. There are two reasons why I did that. First thing, as I mentioned, I wanted to isolate my XD cluster from the system cluster. Second thing is I wanted to highlight the node affinity and show you how I can force each pod to get placed on a specific node. So how are we going to access the stateful pet set pods? So that's a very interesting question. So stateful pet set pods will actually have the DNS name that you can resolve. So let me take a chance and switch to the demo again, and I want to give it a shot. Okay, so let's do this. kubectl exec it MySQL 1, or actually let's go to MySQL 2 bin sh. Okay. I guess Okay, I don't have time to really do this, but I can actually get into the MySQL pod and ping the other pod. So you can pretty much ping one pod from the other using the name. So I need to do an inspect, get the container name, and actually exec into that. I don't have time, but you get an idea. So one pod will talk to the other using the DNS name, which is mediated to the headless service. There are questions on the recording. Yes, absolutely. It's going to be up on YouTube in a couple of days. We'll share the link with all of you. There's a question on WordPress static content. Where is it stored? This is from John. So the static content is also going to the NFS share. So everything is completely isolated from the pods. So they're completely stateless. There is a question on how do we handle username password access without secrets? It is, okay, that's a tricky one. The best mechanism, the best practice for using sensitive data like usernames and passwords is using secrets. If you don't want to use it, you have to really do a workaround. I don't have the best answer for that, but secrets is the most preferred way of injecting sensitive data into your Kubernetes deployments. Okay, so there is a question from Anil. Can you show the kubectl get service and show how the front end connecting to MySQL service IP? Again, I don't have time, but it's a straightforward one. You can basically, so when you actually look at the number of services, so this service, which is MySQL, this is going to be the service that WordPress will access. And this is going to be the endpoint that will route the request to one of the stateful pods. So it is pretty much the same service that will be used by any internal client for getting bounds to one of the stateful pods. Okay, so we're almost done with this session. So thanks once again for joining this, and those of you who have been attending this series regularly, thank you so much. Thanks once again. We are committed to bringing you high quality content, and as you notice, the content is going to move into more advanced concepts. So stay tuned and keep an eye on cube.live. We are going to update that with the upcoming webinar and the registration page. And of course, all of you will receive an update from us with links to the source code, slides, and the video, along with the link to the next webinar registration site. So thanks once again. Have a great day. See you in the next webinar.